Villa Circle. Your next problem is coming, the number 31 in fluid statistics. It says 31. Find the absolute pressure absolute pressure and gauge pressure at points A, B and C as shown in figure given 1 atta is equal to 10 to the power 5 Pascal. That we know already. Anyhow, the diagram, there is a container. It contains 3 liquid, layer by layer. It is mercury. The second layer is water, and the third layer is kerosene. Okay. Point given here, somewhere it is A, here somewhere it is B, and at the bottom it is touching is C. The respective height of this point from the top flat surface of the liquid, it is 1 meter from point A, and from this surface to this point it is given is 1.5 meter and these dimensions are given 0.5 meter, this dimension is given 2 meter, this dimension again is given 2 meter. Okay, and the densities respectively, this is kerosene 800 kg per meter cube, this is water means 1000 kg per meter cube, this is rho of kerosene, water, rho of mercury 13600 kg per meter cube. Okay, these are known. Okay, so now we have to find the absolute pressure and the gauge pressure. So as you know, on any surface, this is atmospheric pressure, always will act P atmospheric. So my any pressure at in any height, let's say any height H, my pressure formula is pH is equal to P atmospheric plus H, rho and G. This is the basic formula. Where in this is absolute pressure, this is atmospheric pressure, and this is your gauge pressure, that you know from the theory itself. Okay, now there we have the theory is given on the basis of only one liquid. But what about all this liquid? If it is a different liquid is acting, what would be the value? Whether I can straightway use this formula or not? Okay, so that so many questions is coming, because if I want to say use this formula, the P atmospheric will come on the surface that is coming in contact with the atmosphere. So this will be the part, it will be applicable when I will calculate this. But then after this part, it will be variable when we vary height. Now in that case we are not varying this part, the density. But if you go on dipping yourself, you will see that height is automatically increasing. At the same time, this is also changing. So straightway I cannot use this formula. But anyhow, if you know the basic formula is this, where you know this is your absolute pressure. So this is and this part is your gauge pressure. Now they also said in a different way, where you have to find the absolute pressure and gauge pressure in the particular points. When you will go on reaching these points from the top, we have to get the. So first my concern is to get A. So for that I need to have its height of h. So what is that from the surface, the top surface? This is 1 meter. Okay, this is done. What do you guys know? Because I am where in the first liquid where only kerosene is available, no other fluid is touching for point A. So the density of kerosene only will be applicable. Okay, so that is 800 kg per meter cube. These are the parameters needed. And what else? P atmospheric, the P0, the P atmospheric, that will be needed. So this much. So then absolute pressure at A is equal to your P atmospheric means P0 plus H of point A, rho of the liquid, that means kerosene, in N to G. This will be the case. So this part is your gauge pressure. If I calculate differently, so the gauge pressure, that means P gauge. So P gauge is equal to H, that means 1 into rho of kerosene is 800 and 1 is in meter, so I need not to change this density unit. This is meter, this is SI unit, this is also in SI unit. In this case G will take in SI and round off to 10 will take for our calculation purpose. So this is nothing but 8 into 10 to the power 3. This is the pressure, gauge pressure. So gauge pressure at A. So that one part of the answer for A is done. Now next, this will be used here. So what is the atmospheric pressure in SI unit? That is equal to, atmospheric is what? 1 atmosphere is 10 to the power 5 Pascal, and this is 8 into 10 to the power cube. This is the Pascals also, because this is in Newton per meter square. Whatever I will get here, I will getting 10 to the power 5 Pascal for atmospheric pressure, plus if I am to convert in 10 to the 5, that is a 0.08 into 10 to the power 5. That will come into the same unit. This is equal to 1 into 800 into 10, so 8 into 10 to the power cube, that is in Pascal. Okay, Newton per meter square, that is Pascal. I am converting into 10 to the 5, that means 2 decimal will go here. So your gauge pressure is this, and your absolute pressure is 1.08 10 to the power 5 Pascal. Okay, so for A point, this is the absolute pressure, and gauge pressure at A is equal to how much? 8 into or you can say 0.08 into 10 to the power 5 Pascal. So the A part is gone. Now second set, when I will reach B. So let me check what will be the case for B. First thing is height. Height of B is how much? This you know, 2 up to this, from this it is 1.5. So total height is 2 plus 1.5, that is equal to 3.5 meter. That is done. Now what is the pressure here? I will get the pressure here can be calculated by pressure for that kerosene total column and the pressure for this much of the water column. So my total pressure will be the P absolute at B is equal to P0, atmospheric pressure will be there, plus pressure due to the kerosene complete of height how much? 2 meter. This will the complete column will act there, plus pressure for water, the next column is water, but the height I will consider 1.5 meters. So this will be the case. Here, what is your gauge pressure? So gauge pressure will be this part is your gauge pressure for B. The gauge pressure for B will be the P for kerosene of 2 meter column plus P for water, which is a 1.5 meter of column. So this is 2 into rho. Rho of kerosene is 800 plus water means how much? 1.5, and rho is equal to 1000. Okay, this is the pressure H, rho, and for whole thing G will be common because G is applicable to anything in a same manner. So this is 2 into 600, 1.6 into 1000 is 1.5 into 1000. So that means 3.1 into 1000 into the 3 into G is equal to 10 again. So that means is equal to 0.31 into 10 to the power 5 Pascal. This is your gauge pressure for B, and absolute pressure for B is equal to 10 to the power 5 plus 0.31 into 10 to the power 5. So all total this is 1.31 into 10 to the power 5 Pascal. This is your absolute pressure for B. Okay, next come your point C. So point C, height for point C is equal to 2 plus 2 plus 0.5. So that is equal to 2 plus 2 plus 0.5 because that is in the bottommost part. So 4.5 is the height per meter. So again absolute pressure for C is equal to atmospheric pressure plus pressure due to kerosene plus pressure due to water plus pressure due to mercury, because everything I am taking the full column. So this is 2 meter, this is 2 meter, this is 0.5 meter. So here this is your gauge pressure, P gauge. So this is equal to, if I calculate the P gauge is equal to H into rho is 800 plus H into 1000 plus H into 1360 whole into G. So that is equal to 1.6. This is equal to how much? 0.0 cancelled 5. This will be 1600 plus 2000 plus 50056 33 13 15 plus 3 18 1 5 1 5 1 is 5 and 6, this much. So all total this is equal to 0 0 0 8 0 6 14 1 6 2 8 9 10. So this will be the case. So if I convert it is equal to 1.04 into 10 to the power 5 Pascal. So this will be the case of gauge pressure. Now what is your atmosphere is 10 to the power 5 plus 0.104 into 10 to the power 5. So all total it is how much? It is equal to 1.104 into 10 to the power 5 Pascal. So this is the three different part of this sum where consecutively I have got the gauge pressure and the absolute pressure. Understood? Okay, fine. I'll move on to the problem number 32. 32 says find the pressure in the air column at which the piston remains in equilibrium assume the piston to be massless and frictionless. Assume the piston to be massless and frictionless. So let me show you the arrangement that is we are working with. A kind of vessel having few legs of this kind, where one leg is being operated with a piston, moreover it is a piston cylinder, you can say. This is the piston and this is the part where air is filled. So this is the cylinder, air operated piston cylinder, you can say. The length of which from this to this is 1.73 meter. Okay, up to this, the bottom of the piston. There is a point B which is matching at the same datum level. This is your datum. This is datum. The liquid column here is up to 5 meter height. This is your water, and this part up to piston, this is kerosene, this is water, this is given. This is at 60 degree given. The kerosene specific density is 0.8. This is specific density is given, or the density, you can say the density, or this is this much of unit is not given, but you can understand this is gram per centimeter cube, or equivalent to 800 kg per meter cube. Okay, this is standard 1 second, whereas water having in the same SI unit, if I take kg per centimeter, kg per meter cube. This is all are standard, you need not to vary. There is another point with which if I extend the datum level crossing these two legs, they will cut some point A and B that are in the same elevation with the datum. These are the details given. Okay, so what is the requirement of the sum? Sum required that find the pressure in the air column at which the piston remains in equilibrium. That means you have to find the pressure inside this, so that the pressure, whatever it is being created through this water column and this kerosene column, whatever the pressure is exerted this side, let's say this is P1 from this side, and the air pressure from P2 from that side must be equal, so that this piston will not move anywhere. Why it will not move? The piston, the both sides, the cross section is same. That means the area multiplied by the P1 exerted from the bottom, and area multiplied by the P2 which is exerted by the air pressure entrapped into the cylinder, by which this is in equilibrium. The forces are same. So these are the concept. Okay, fine. Now let's say this is denoted by PA, the air pressure inside the cylinder. This is your atmospheric pressure P0 or P atmospheric, you can say. Okay, now what do we know as per our thumb rule? the pressure at same elevation for same fluid is same. So that means if I consider this partition where the kerosene and water is just making some surface, a contact surface, whereas the below this level is water. So if I just consider the level where that water is touching with the kerosene, at that point these are of same liquid. So that means at A and B we consider same pressure. Why? Due to same liquid and same elevation. Okay. Because this and this condition is fulfilled when the complete arrangement is in static equilibrium. Condition is in static equilibrium. So these are the condition fulfilling, as piston is not moving, so you can understand that total liquid or the total arrangement of the fluid is in steady state or static condition. In static condition, we know 2 points of having same elevation, of having same liquid are in same pressure. So from there, the pressure at A is equal to pressure at B, you can say. So this is the first and foremost concept. Now, how that pressure of A can be denoted? This is the atmospheric pressure P0 plus the pressure due to this water column. Here it is water, this is only kerosene. So this is H into rho of water into G. So this is the case. In PV, let us see the pressure created by this PA, the pressure inside the cylinder, plus the length of this is 1.73. But what do we know? Pressure at any point is the vertical height into rho into G. So what is the vertical component of this length? This length, if I say this is L, so this L, and if I see it as an imaginary triangle, so this will be the vertical height. So now what is this component? If I say this is H, so H is equal to H by, this is a right angle triangle. Let me draw the triangle. This is L, this is H, this is base, this is H, this is L. Okay, so this is 60, as you know, this is 60. So if I take sine of 60, that is equal to height upon hypotenuse. So what is your H here? L sine 60. This is the height you have to take. So now instead of this, what we will write? L sine 60 is my height. Rho of what? Rho of kerosene will come here. Of kerosene into G will come. So this is my complete equation. Now what is this? This is the atmospheric pressure. This is 1 atmospheric pressure, 1 atm. This is my case. So these are in Pascal. This the pressure whatever it is coming, if we calculate, this will be the this will come as in Newton per meter square, that means in Pascal. So this, if I consider for 1 atm, is how much? 10 to the power 5 Pascal. So straightway you can write 10 to the power 5, because everything I will get in Newton per meter square, that is Pascal. So Pascal of atmospheric is 10 to the power 5. 5 into rho of water is 10 to the power cube, and G we are taking for the roundness, it is 10. Here PA unknown, L is how much? 1.73, and L 60 is equal to root 3 by 2. Okay, this is equivalent to, you can say, almost root 3, because root 3 is equal to what? 1.732. So if I round up to this, So this you can consider as root 3. So I will eliminate the decimal calculation. I will put it in this form, root 3. Rho of kerosene, it is 800. So I will put 800 into G is 10. So removing all other things from here, what will get? I will get 10 to the power 5 here, plus if I want to convert it 10 to the 5, then I have to take point here. So this is 0.5 into 10 to the power 5. I just want to bring everywhere 10 to the power 5 part, so that calculation will be easy. Plus root 3 into root 3 is 3. 3 by 2 into 8, and this is 10 to the power cube. So I will put it like that, 10 to the power 3. So I will rub this part. Now I will not keep this here. So this is 1.5 into 10 to the power 5, that is equal to PA plus 4, 12. 10 to the power 5 means 1.12 into 10 to the power 5 you can put. So then PA is equal to how much? 1.5 minus 0.12 whole into 10 to the power 5. So that means if I deduct this, 1.38 into 10 to the power 5 Pascal, this will be a answer. And 10 to the power 5 Pascal is equal to approximately 1 atom or bar. So you can put it like that, approximately this much of bar. Okay, if it is needed in bar. So this will be a answer. Okay, moving to the next, that is 33. 33. A weighted piston, a weighted piston. In the earlier problem, there one thing is given that I have not discussed, but that is not even contribute anything in the problem. Piston was massless and frictionless. That means massless means the whatever the weight of the piston, it will not contributing any deviation in the pressure in the system, that is there. And friction, that is, there is no resistance force acting against the force being created by the PA to diminish its value. So frictionless, and this is the ideal condition that is given. If it is not given, then either you can declare it. If it is no data is being given to calculate such forces, then you have to declare considering that piston is weightless or frictionless. So that also can be possible. Okay. The weighted piston confines a fluid of density rho in a closed container, as shown in the figure. The combined weight of the piston, and combined weight of the piston and piston and weight, that means some additional weight is kept on the piston, that all together is weighing 200 Newton. This much force is creating, so weight is in kg force into 10, so that means 20 kg force is the weight, and while converting into Newton we are multiplied with 10. Okay, and the cross sectional area of the piston is A equal to 80 centimeter square. Find the total pressure at point B. The total pressure at point B if the fluid is mercury. The fluid is mercury and H is 25 centimeter, rho of mercury is 1360 kg per meter cube, that is there. What would be the pressure order? What would an ordinary pressure gauge read at B? What an ordinary pressure gauge read at B. Okay. Now the arrangement is somewhat given like that. This is a bit. Let me draw this part first. There is a height difference that has to be understood properly. This is the piston on which a weight is kept. This weight is kept. Okay. And this piston when it is acting on it, so that means I have to take somewhat less height, and this is the gauge, I suppose it is given there, the gauge, in the center line of the gauge means this is not that much of high thickness, means this is gauge. Okay, this is gauge, and the center line, the deviation is, this is H. The height difference due to which the pressure is being created in the gauge. This is the gauge. Okay. So this is the height difference. If I take from the center of this is height difference. Okay, so let me read it out again so that it will be clear. A weighted piston confines a fluid. This is the fluid inside this. Okay, of density rho. The density is rho. Okay, in the closed container, and shown in the figure, the combined weight of the piston and the weight, the piston having some weight plus the weight, all together giving 200 Newton of force. And the cross section of the piston is 80 centimeter square. The cross section is 80 centimeter square. So that means if I convert into meter, so 80 by 1 centimeter is 1 upon 100 meter. So that means 100, this much of meter square. Okay, Find the total pressure at point B. Where is point B? Oh, this is point B. So this is the point B, which is taken at center. At point B, what is the pressure? Then point B to this piston height is given as H. Okay, due to it. So so point B, the pressure you have to find the pressure of fluid, and height is this H is given as 25 centimeter. That means this is 25 upon 10 square meter. Okay, and density is given. So the pressure here, this as because this is same liquid, so at this point the pressure here P of B, if I take, this is the pressure which is pressure due to this column, H into rho of the liquid into G, this much pressure, plus this pressure plus the weight of the thing divided by the area. This would be the equation. The pressure here, if I take the same line, horizontal line, the pressure here and pressure at this point, these are in same, and liquid is also same. The pressure here to the pressure here will be same. So pressure of B here, there is no atmospheric pressure is acting because this is a closed one. Atmosphere is only the pressure B is acting. That is equivalent to the height. There is a liquid column of height H creating some pressure plus the weight of the system, piston plus the weight together is acting on this cross section A. Okay, so now what is that? H is equal to 25 upon 10 square into rho of liquid. That means the liquid is, the density of rho is closed and continuous one. And where is this mercury? There is two liquid or semi liquid. The weighted pressure of the fluid, the density is closed container shown in the figure, and the container. So that means if it is given that the density of mercury is given and there is no mention of the weighted piston condenser fluid density, the rho, and then at point B, if the fluid is mercury, at point B, if the fluid is mercury, at point B there is a fluid is mercury, and apart from this will be added with some other pressure because this is free end, so there will be another pressure of atmospheric pressure. This has to be added there. So this I am not added earlier because this is closed system, but whereas the weight due to this water column and the pressure due to the atmosphere, because there is nothing said that atmospheric pressure can be nullified. This is also there, and at B the density, the fluid is said to be mercury. Mercury, what it said? Find the total pressure at point B if the fluid is mercury. That fluid is said to be mercury. Okay, fine. So that the fluid that is contained here is mercury. So we can take the rho of mercury directly. So rho of mercury is 13.6 into 10 to the power 3 into G I am taking as 10. Further, weight of this is 200 Newton. So that means 200 into, I will write it 200, and this is in SI unit, so no need of change. And there area is, then area if I take in meter square, so that is Newton per meter square, whereas that thing is changed, converted into meter square. 80 divided 10 to the power 4 will go up, 10 to the power 4 plus along with 10 to the power 5 Pascal for your atmospheric pressure. So all total, this is, if I cancel 10 square, 10 will be there, 10 square will be there, 13.6 into 25. So that means 150, 15 will be there, 75 plus 15, 90, 9 will be there, 25 plus 9, 34. So 34 will be there first part. So 34 if I multiply 3400, 13.6. So there are 1 point, so 340. So 340 into 10 to the power 2 will be there first term. Second term, this one will cut. 4 2s are 4, 5s are 2.5. So 2.5 into 10 to the power 10 to the power 4 plus 10 to the power 5. So this will be the case. So now I will drop this part. This is done. So calculation, this is 3 point. So if I want to make it 10 to the power 5, so this will 3 part will go there. So 0.34 into 10 to the power 5 plus 0.25 into 10 to the power 5 plus 10 to the power 5. Okay. So this all gone. 0.11 will be there, and this together 0.59. So 1.59 into 10 to the power 5, and that's in Pascal, will be the pressure at B. Okay, so this will be the pressure at B. Now this can be said to be 1.59 bar or eta approximate. Okay. So this is the end of this session. In the next session I will move on to the problem number 34. Thank you for now. Good night.